So the first talk today is by Tony Lanzirotti, who has a PhD in geochemistry from Stony Brook University. He's worked for the University of Chicago's Center for Advanced Radiation Sources for more than 20 years, overseeing the development and operation of X-ray spectroscopy beamlines at the APS and the NSLS. He's also the chair of the National User Facility Organization from 2011 to 2013, and he was even asked to testify before the U.S. House of Representatives Science, Space, and Technology Committee in 2012 about the benefits and significance of research conducted at U.S. national user facilities. So Tony will give a talk on an overview of synchrotron facilities in high temperature geochemistry. So Tony, take it away.
Great, thanks, Paul. Okay, everybody can see that well. All right, so what I'm going to do today is much like Joanne did yesterday. I'm going to sort of set up the talks, for today's session. Sort of day two. I think our focus on the types of geochemistry that we're going to talk about today are a little different than yesterday. From my perspective, why these types of sources are so useful in studying geosystems is the given extreme heterogeneity that we see in geologic studies. Geologic and cosmochemical systems have this extreme inherent heterogeneity from the molecular scale all the way up to planetary length scales or even solar system scales. We talk about cosmochemical studies. And one of the most significant challenges that I think we all have as geochemists is modeling and understanding these heterogeneous global systems with methods that are actually able to bridge those length scales, to take what we see at the mineral and molecular level, and then allow that to model what's going on for geologic formations or planetary systems. And these coherent bright X-ray sources for geochemical analysis enable really a robust understanding of complex reactivity, and they're sort of unique in the types of things that they can help us understand. So if we talk about just in terms of a few techniques, this isn't all the techniques that are available at synchrotron facilities, but we have things like chemical imaging and microanalysis. So the various different kinds of soft and hard X-ray microprobe work, microspectroscopy, X-ray fluorescence and X-ray absorption spectroscopy, for electron spectroscopy, X-ray emission, and then coupling what we get for these sort of chemical probes with diffraction and scattering that couples the chemical data to what's going on mineralogically. Some of the applications that these techniques can then be applied to in geology, we have things like petrology, sedimentary igneous metamorphic systems, cosmochemistry, scaling that petrologic information up to Earth evolution, talking about plate tectonics, biostratigraphy, even paleontology, and then looking at things like economic resources, long-term storage, looking at critical resources, fluids and fractured media, ore deposit work, oil, gas, nuclear exploration, geothermal resources. So I think all the speakers that we have scheduled for today are going to touch on various different aspects of these types of geochemical applications and these techniques. Okay, so what I'm going to do now is I'm just going to give sort of a brief overview. And again, it's not complete, but some of the unique capabilities of synchrotron methods for geochemical research. And I think many of these are just sort of, touch on the things, again, that the speakers are going to highlight today with more in-depth detail and really give you a sense of how exactly these techniques can be applied to geological work. So one of the things that is sort of unique about synchrotron analysis is that it allows you to do high resolution trace element analysis. And there's many types of probe techniques that you can do trace element analysis with. But one of the things that's sort of unique about using X-ray techniques is that in sort of the broad perspective, they're relatively non-destructive. The amount of power deposition to the sample is actually relatively low. An example of the application of this type of technique is looking at interplanetary dust particles. So this is some work that's been done in synchrotrons for many years now. NASA Johnson Space Center curates thousands of dust particles that have been collected at the high end, the stratosphere. And this is just an example here on the left, an SEM image of one of these very typical sort of interplanetary dust particles, scaled by here is only a micron, so these are very small. So with synchrotron X-ray microprobe, for example, you can get trace element analysis of these individual dust particles with detection levels in the parts per million or parts per billion range. So in the lower left, this is a very standard type of energy dispersive spectra that you might acquire from one of these single interplanetary dust particles. And a single dust particle of this mass is only about 30 picograms in mass. And we can get very good elemental concentrations from individual small particulate matter, right? Another example where this is useful is the analysis, and I'm going to talk about this in the next several slides, in situ analysis of materials. And that's, again, something sort of unique that these X-ray probes allow you to do that is difficult to do with other types of probe techniques. This is an example talking about NASA Stardust missions. Stardust was the first sample return mission since the Apollo mission, sent to collect samples of cometary dust. So we had a space probe, flew through the tail of Comet Belt 2, and collected samples of dust in very low density aerogel materials, silica aerogel. So why synchrotrons are particularly useful here, synchrotron analysis, is it allows characterization of the minute particles that are saved in these materials. So in the lower right, you see a keystone, a piece of the aerogel that's been sectioned out of the material, and you see the image of the track. This is about 4 millimeters long. And synchrotron analysis allows you to look at the particles in the aerogel without having to do particle extraction. And this is something that became very useful and became very apparent from the Stardust mission, such that it's actually now what ends up happening is that synchrotron analyses end up being one of the first steps in preliminary examination of these types of materials. So again, it was applied to Stardust, but we have sample return missions from Hayabusa 1 and 2. OSIRIS-REx is coming. They've made new samples analysis from new materials available from the original Apollo missions, and these are all being applied. And just to give you an example of this, on the right, this is an image of one of these tracks in Stardust aerogel. So you can see here, this is the particle entered from the right. This is the track. And you can see that these particles being captured at speeds of 6 kilometers per second disaggregate on entry. So if you want to get a good sense of really what the composition of the original impacting particle was, you need to actually analyze the entire track. And synchrotron techniques let you do this in the aerogel media, again, without having to extract the particle. And on the left, you see X-ray fluorescence maps with high spatial resolution, high detection sensitivity of what the chemical composition in these tracks were. You can also extend this to imaging large materials. So one of the things that, again, synchrotrons microprobes have allowed us to do is do high speed, high resolution trace element megapixel imaging. Again, this is enabled by the high brightness of the synchrotron source, but coupled to actually a new generation of spectroscopy detectors and amplifiers that allow researchers to generate megapixel trace element maps with ppm concentrations today with only minutes to hours. And this is just an example of two types of images. The one on the left, this is from Chris Ryan at CSIRO. They, along with Brookhaven National Laboratory, helped develop this Maya detector, high-speed detector. So this is an image of the distribution of iron, bromine, and arsenic in a sample of a gold deposit from Western Australia. Scale bar here is 1 millimeter. So again, this is sort of the needle in the haystack kind of approach, that you can image trace element concentrations in geologic materials at large scale with very high spatial resolution and very high detection sensitivity. On the right, this is an example from Jen Sider, U.S. Army Corps of Engineers, looking at lead remediation in contaminated soils. And this is a section in soft material. This is a section of an earthworm where you're actually able to image the distribution of not only major elements, but also trace elements like lead, again, very rapidly at very low concentrations. An example of how this is applied to sedimentary systems, and I think this is something that I think David Fike is going to sort of touch on a little bit today. This is some work done a number of years ago by Troy Raspberry at Stony Brook University and Tony Dixon, doing large area mapping of the strontium to calcium ratio in echinoderms. So it's known that in the Phanerozoic, there's been sea level changes in the strontium to calcium ratio changes and as a function of geologic time. And so they have used the strontium to calcium ratio in carbonate materials to tell us something about potential sea level changes. But in fossilized materials, you have the strontium incorporated not only in the primary biogenic calcium, but also in diagenetic materials that are infilling the fossilized materials. So with these kinds of rapid, large-scale X-ray fluorescence mapping, you can then use things like principal component analysis to separate out what is the biogenic calcite from the diagenetic calcite, and then only look at that strontium to calcium ratio and say something about the evolution of oceanic strontium levels over time. In igneous petrology, micro-XAFs has become extremely powerful. And one example here that I'm going to talk about, and this is something that I think we're going to have Mary Jo Brounce and Aaron Bell highlight a little bit later today, is using the valence state of redox sensitive elements to tell us something about the oxygen evolution of magmatic systems. So in silicate melts, the valence state partitioning in the melt varies as a function of oxygen fugacity between the crystal and the melt. So in the right, this is a figure that was modified from a figure put together by Jim Pike in 2005. But if you have a series of elements that in magmatic systems will change their valence as a function of oxygen fugacity, and if you think about this in terms of log FO2 relative to iron wustite buffer, that basically covers the log FO2 for the entire solar system. So things like vanadium can change their valence state as a function of FO2 from basically iron wustite -9 down to iron wustite -10. So with microspectroscopy, the ability to be able to collect X-ray absorption spectra with very high resolution in geologic materials, then we can actually look at get a sense for what the FO2 changes in that magmatic system in very, very small objects. So in the lower left, for example, this is something that's become extremely popular. It's an image from Liz Cottrell and Katie Kelly. You can look at, for example, at melt inclusions, which are very small bits of magmatic melt that has been trapped in igneous phenocryst and crystallized. And then you can do micro X-ray absorption spectroscopy to look at the valence state and then couple that back to the change in valence and the change in oxygen fugacity. And this is just one example looking at vanadium. And even if you've never done X-ray absorption spectroscopy before, what you see here on the right, this is a standard, very typical Zane spectrum for vanadium. Here you have the normalized intensity on the left scale, and this is the incident beam energy increasing to the right. And this is for a series of experimental charges with differing synthesized at different oxygen fugacities. And you can see that the spectra show very distinct, very strong differences as a function of FO2, as a function of the valence, extending from vanadium 3+ all the way up to vanadium 5+. You can then make a calibration curve of, if you know the valence state or the oxygen fugacity of the experimental system. So here on the lower left, delta NNO nickel oxide buffer experimental versus that which you predict. You can make a calibration curve, and then you can analyze natural materials. Here on the lower right, these are some glasses from recent Kilauea eruption at Pahoa. You can analyze those glasses, measure the X-ray absorption spectra, and then calculate the oxygen fugacity at which those glasses equilibrated. You can also take advantage of those spectroscopic measurements to look at valence state in an imaging approach. So one of the things that, again, this is sort of unique, is that you can do chemical imaging of the oxidation state of different elements. So in this example, this is upper left, this is an image from Sam Webb that shows you the difference in the spectra for arsenic in different oxidation states. You can see, again, they're very, very distinct. So you can collect a series of images at different energies and then image the valence state of the different arsenic species in geologic materials. So in the left here, this is a paper from Barbara Etchman and Ann Min. This is looking at piezolytic regolith, and so where they've actually imaged the arsenic oxidation state, and then being able to correlate that to economic elements, so like gold, to understand the ore deposit evolution of the system. And today, advances in our ability to generate smaller and smaller beams. This is something that Ryan talked about yesterday at NSLS2. This is from the HXN beamline, which is now able to generate spot sizes of 5 nanometers doing hard X-ray work. Again, this is upper left. This is an image of the different arsenic oxidation states, but this is some work from Florence Ling, and Catherine Peters is going to be on later this afternoon. And I think she may highlight some of this type of work as well, looking at contaminants and hypersaline wastewaters. So what they've been able to do is that in an experimental system, actually look at the precipitation of barite crystals of different saline contents. And so these crystals are extremely small. So scale bar here, and on the right here, this is a phase contrast image of a single precipitated barite crystal. And then you can image the distribution of arsenic 5 here with nanometer resolution. And one of the things that they've been able to show is that the arsenic valence is zoned, the arsenic concentration is zoned, and that only occurs at very high salinities, which is important for looking at evolution of these systems in wastewater systems, for example, or deep fractured systems. We also have Marianne Louvel going to be talking today, and I think she's going to be highlighting one of this type of work. One of the unique things, again, about you can also do with X-ray absorption spectroscopy, making use of the penetration depth of X-rays, is actually look at the speciation of materials buried within geologic media. So, for example, you can look at liquid fluid inclusions. This is some work that was done by John Mavrogenis looking at fluid inclusions trapped in quartz. So, you could do a standard heating freezing analysis. Take a natural fluid inclusion, change the temperature, look at the change in the composition of the copper, for example, in situ at different temperatures, and understand something about how copper is transported in natural chloride systems. And again, this is something that really is unique to synchrotron analysis, which you can't really do with any other type of analytical technique. Similarly, and again, this is something I think that Marianne's going to touch on again today, you again make use of that penetration depth of X-rays to look at systems within environmental cells. So, for example, within diamond anvil cells, this is some work that was done by Schloten et al. In hydrothermal diamond anvil cells. So you can have a material of geologic interest. Here they have hematite and magnetite and fluid. You can change the temperature, you can change the pressure, and then you can measure the X-ray absorption spectra to look at the change in the speciation here of iron. But you could do it with other species in real time, in situ, in operando, as you're changing the environmental conditions of the system. Again, this is something really unique to be able to do with synchrotron techniques. We talked about this a little bit yesterday, talked about STIXM analysis. There's also something that's sort of unique to be able to do with these types of synchrotron systems. And with STIXM being able to look at the evolution of organic material, the species of the speciation of organic material in geologic systems. This is an example from Ito et al. Looking at extraterrestrial materials. And extraterrestrial materials collected from comets and asteroids often contain very small, tens to hundreds of microns in size, complex intermixtures of both ultrafine minerals and or organic components. And with STIXM, you can go in and with nanometer resolution, so again, this was talked about a little bit yesterday, how STIXM works, but you're looking at materials that's only nanometers thick. You look at the transmitted soft X-ray energy, and then from that being able to characterize here in the lower right, you can get these different X-ray absorption spectra to tell you what the different organic components are in that material. And again, that's something really unique to being able to do with these types of instruments. Another thing about using the penetrative depth, and Joanne sort of highlighted this yesterday, talking about tomographic techniques, and the tomography that she talked about yesterday was just sort of full field absorption tomography, but you can also use those tomographic techniques to look at the chemistry of materials. So this is sort of a first generation tomographic analysis where you use a focused beam, raster a sample through the focused beam and rotate it, and then you can collect various different types of information. You can look at energy dispersive spectrum, look at trace element composition. You can do this with actually absorption spectroscopy. You could do this with diffraction. And then from that, you can actually generate a three-dimensional image of the trace element contribution in a material with very high detection sensitivity here. This is some work from Troy Raspberry and Stephen Cox, looking at apatites. These are apatites that are trying to do thermochronometry on. If you're not familiar with thermochronometry, you're looking at the closure temperature of radiogenic helium isotopes as the materials are uplifted. And so you can see this is a very small apatite crystal, only about 100, less than 100 microns in diameter. And then here, to understand how the radiogenic elements are produced, you look at the distribution of yttrium at uranium at 10 ppm concentration limits without actually having to physically section the sample at all. And then I just want to end with talking about multimodal spectroscopies. So again, many beam lines at synchrotron facilities are actually starting to combine these techniques, being able to do them all at the same time. So X-ray absorption spectroscopy, X-ray diffraction, X-ray fluorescence. This is some work looking at fractured carbonate media. This is from Ellis 2013. Again, this comes out of Gasper and Peter's group, but I think this is something that Catherine and Jim Evans and Caitlin Crouch may talk about some of these kinds of analysis today, being able to look at the chemistry within fractured media. This is some work from Karina Lang and Steve Mihak at the Canadian Nuclear Regulatory Commission. Joanne showed this slide yesterday, so I'm not going to dwell on it too much. But again, being able to couple techniques, this is looking at uranium mine tailings. You can collect full X-ray fluorescence maps, look at elemental composition. And at those maps, you can have X-ray diffraction data at that same point. So you can basically sum areas to look at mineralogy, look at how the changing chemistry is coupled to that mineralogy, go in, do fine X-ray absorption spectroscopy to look at changes in speciation. Okay, so I'm just going to end on this slide, sort of highlighting that we're going to have this roundtable discussion at the end of the day. And so, as you listen to the talks today, think about what sort of the broad questions that we want to talk about and we want to highlight. So what are like the major challenges and limitations in your ability to use synchrotron methods in geochemistry? Is there sufficient access to beam time for geochemists? Are there sufficient training opportunities available for novice users? Workshops, schools, what are the things that you want to see? What types of new publications would be useful? We'd like to have some kind of publication come out of this workshop. And in fact, back in 2006, there was a special issue of Elements on this. There was also a RIMG volume in 2002, but that's quite a long time ago now, right? So that's something that we want to update. Okay, Paul, I'm done.
Great, thank you, Tony. That was a great introduction. We have time for some questions. If you have any questions, please put them in the chat box. There was already one question from Abby Kavner asking. She was saying she was curious: are sample return storage facilities being planned in proximity to synchrotron sources?
The answer is no, that I am aware of. At least for NASA missions, typically what happens is that Johnson Space Center does that curation. But for example, right now we have some funding from NASA to look at these Apollo samples that were collected and stored by NASA for 30 years in anoxic, frozen conditions. And they're just making those available now. And that was actually very insightful of NASA to do that 30 years ago, saying that, in 30 years is going to be analytical techniques that weren't available. So one of the things that they're doing is they are open to the community, those of us that are involved, going to JSC in their clean rooms and helping with the sample preparation.
Oh, cool. Then, so I had one question. I'm curious, when you're dealing with these tiny particles and the very few, I think you had on your slide saying that those concentrations were corresponding to 30 silver atoms, if I understood it correctly, in some cases. So how do you deal with statistics and like significance on such small numbers when you're doing these things? It must be a bit of a challenge.
It is a bit of a challenge, and we always get the question about quantification for these types of analyses, right? And we have lots of experience, decades of experience in X-ray fluorescence and trace element analysis from other probe techniques, so that's fairly well established. But often the complexity for what we do is, again, that it's an advantage to have the penetration depth that X-rays provide you, but it also is a bit of a complexity in that you do have to think about in a material that's, let's say, 30 microns thick, right? X-rays are going to go completely through that. The absorption characteristics of the X-rays and the fluorescence that you're going to detect is going to change depending on the absorption coefficient of the minerals, how thick the sample is. So all those things, it's an added complexity that has to be thought out. I think we have a fairly good understanding of that, but in some materials it can get rather complicated.
But it's just remarkable. I mean, to be able to count atoms is great. So there's one more question in the chat. I think we're gonna. Can you respond to that question
Yes.
afterwards? So we want to try and keep on schedule. So thank you very much, Tony.
Yep.